Welcome to this chapter of our CUDA Developer Tools series on Nsight Compute. Today we will take a look at the memory workload analysis. My name is Maximilian and I am a developer technology engineer at NVIDIA. GPU workloads often suffer from being heavily memory bound, with ever-increasing compute, especially in content creation where video frames are being streamed through memory with sometimes little processing, like a color adjustment filter. The memory workload analysis section of Nsight Compute helps to guide us to achieve the full memory bandwidth of our GPU and optimize data access patterns to increase the cache hit rate. If you've not seen the introduction to Nsight Compute featuring the speed of light section, you might want to think about starting with Bob's video first, which is linked in the video description. Besides that, I highly recommend watching the linked GTC presentation about the memory hierarchy and memory transactions on an NVIDIA GPU in more detail than I will cover in this video. It is crucial to understand the way memory is requested and what cache lines and sectors are in the context of CUDA. We will start with a theoretical walkthrough of the memory analysis chart where we get an overview of hardware memory locality and memory type. The green elements denote logical units in software, e.g. texture memory with different ordering, or simple global local memory that refers to raw memory. All physical units in hardware are colored blue. Arrow links between physical units denote the amount of read or written bytes across this connection. The color of the arrow provides some insights into how far we are from the peak throughput of this interconnect. Via the drop-down menu, we can also switch between the total bytes or the peak throughput percentage labeling of a connection. Upon a memory request inside our kernel, depicted on the left, we check if the requested sector behind an address is already present in L1. If not, we fall through to L2 and check for the existence there. If none of the above contained this sector is fetched from device memory. Our L2 cache is the point of truth for all streaming multiprocessors. What I mean by that is that all memory traffic has to go through L2, including PCI copies or device memory writes. Only if a sector to read is already present in L1, the L2 cache is not used. The L2 cache ensures that no SM reads invalid data from device memory that has not been written back, as it is shared across the whole GPU, while L1 memory is local to one streaming multiprocessor. We can reduce the traffic between L2 and device memory by increasing L2 hit rate. And we can, following, reduce the traffic between L1 and L2 with a higher L1 hit rate. Of course, traffic can also be reduced by changing the algorithm to simply require less data to be transferred. Those hit rates are important to ensure low latency of memory requests, as fetches from device memory take many cycles. To understand more about the communication between the different types of memory and about how the hit rate is calculated, it is important to understand at what granularity the different units communicate. Cache lines are 128 bytes long in L1 and L2, but any communication on the GPU is done in sectors, whose size is only 32 byte. While on newer hardware, more than one sector can be communicated at once, a single sector is still the smallest communication possible in the memory system. The concept of cache lines is important as we cannot allocate single sectors in cache, but always full cache lines into which we then read contiguous sectors. As a practical example, why cache line allocation is important, we will assume a cache of only 2 cache lines. If we now read a picture in which each row is over 128 bytes long, we see the following. Reading the first entry of the first row and the first of the second row, we would each allocate a cache line. If we now read the third row, we have to invalidate a cache line to read the next. We would not be able to reuse any cache lines. This essentially lowers our possible cache storage to 25%. If we read the same memory in rows rather than columns, we read a full cache line, then the next, and so on. After reading both full cache lines, we again have to invalidate, but we were able to hold on to much more sectors and therefore more values much longer, especially with wider prefetches that transfer 2 sectors at a time. We also increase our latency. The previous explanation does hold for L2 and L1 cache. If we would read 32 consecutive bytes in one SM, we would have a hit rate of 97% in L1. This would result in 0% in L2 because we send only one request to L2, and after that has been executed, all data is present in L1 and will be a cache hit on further requests. If we, on the other hand, have a kernel that reads values with a stride of 32 byte, meaning only the first value within one sector, we get 0% L1 cache hit rate. L2 will only have to reallocate a new cache line for every fourth value when reading with a 32 byte stride, but has to request data from device memory on each request, if we assume no prefetch is happening in this case. The earlier we have a cache hit, the lower the memory latency is, with device memory clearly being the worst case, because this memory is not on chip. We have not talked about shared memory yet, and especially the improvements that it got with Ampere. Shared memory is per SM memory and is effectively L1 memory, with the difference that this memory is not written back to device memory and is meant as a workspace memory. By requesting shared memory, one reduces the available L1 memory. This way, data can be shared across threads in a block running on the same SM, without going through L2. This is also an effective measure to manage L1 cache manually, if the desired caching is not achieved automatically. With Ampere, the load global store shared instruction was introduced, which allows to directly read data to shared memory without going through unmanaged L1 memory first. Just a brief outlook. Preloading data to shared memory is a commonly used pattern for sliding window operators like a convolution. All threads in the same CTA, or also SM, are used to preload data to shared memory. After that, the data is accessed by all the other threads, and the weights are persistent in L1 cache, for example. This already brings us to the load and store address spaces used in our kernel, here shown as green boxes. The most basic loads are global and local loads that will load raw byte data. For surface and texture loads, we can possibly see different indexing schemes, for example, for set-ordered textures. Furthermore, we see the shared load operation for Ampere and later GPUs that we talked about before. It is important to understand the difference between local and global load stores. Any local load and store is usually something we want to get rid of. The origin of these local operations is often due to register spilling, for which I'll have a link in the video description. This means the kernel is not able to keep its working data in the physical register file and has to write back to memory. This has very strong performance implications. Finding the origin of those local operations can be done using this address space column of the memory chart, or by using the source page of Nsight Compute and looking for LDL and STL instructions. The usage of this source page will be covered in a separate tutorial. Looking at it can be very helpful to identify the exact line of code that is responsible for this local access. All absolute values that we see in the memory workload analysis chart are shown in the table below, which I will not go into detail about right now, but rather want to give some example usage on how to use this section. The code for the following example can be found on GitHub and is linked in the video description. We will profile this very simple program to convert an 8-bit PNG from RGBA to grayscale. What we do in our kernel is we load 4 consecutive pixel values, which are our corresponding RGBA values, apply a multiplier to each and add them up to a single grayscale float value. Then we downcast and save it back to our output buffer. For now, I collapsed the optimized versions. Please explore the code for those on GitHub. First, let's make sure we have our theoretical values set. We are reading a 4-channel UNT8 picture of size 3840 by 2160 and write at the same size, but only one channel, UNT8. So we expect a load of around 33 megabyte and a store of around 8 megabyte. While Nsight can give us a good measurement of how far we are from the CUDA device hardware limits, it cannot tell us if our processing approach is suboptimal. This is something we should always keep in mind. I will use Nsight Compute's capability to remotely profile using an SSH connection. We will start with creating a new project and establishing our connection. I usually name my project with a %i in the name. That way Nsight Compute will simply enumerate the profiles I take without overwriting an old file or me needing to remove an old file. To get the memory chart analysis, we have to either select the detailed profile or the full profile. I recommend simply going with the full profile. Furthermore, I also like to import the source in the Others tab, as it will allow me to track my source changes across my profiles, in case I do not version them correctly. Now we can simply hit the launch button. On the first launch, it will upload all needed binaries, which can actually take some time. For me, I've done that already, so our baseline will straight pop up. Before we dive into our memory workload analysis, we can already see in the speed of light section that our memory speed of light is already at 80%. This usually indicates a very well performing kernel. But our compute speed of light is very low. To me, seems lower than expected. Looking at the memory workload analysis section, we see that the link to device memory is at very low peak utilization, judging by its color. But the link between L2 and L1 shows much more data flow than we would expect given our pointwise operation. The cache hit ratio for L2 also seems superb, but things are sometimes not as good as they look, which is why it is important to understand why we calculated the previously mentioned theoretical numbers. We want to know if we are really limited by hardware or if our algorithm is suboptimal. Nsight Compute can only show correct speed of light measurements if the used algorithm is limited by hardware. It cannot tell us if we are doing suboptimal or superfluous processing. What is happening here is that as we read 256 pixels vertically in one block, that each thread requests data for 1 pixel. Assuming an uninitialized cache, this leads to allocating a cache line in L2 and L1, then loading the sector of that line from global memory in which the pixel data is located. As we are processing vertically, we request 256 cache lines and 256 sectors, but we only read 256 times 4 bytes from those sectors, although for each of those 256 sectors we have to transmit 32 bytes. Even worse is that the same is happening for storing our grayscale data. To store data, we also request 256 sectors, store 1 byte to them, and write the complete sector back. We are actually lucky with our problem to not generate even more device memory requests from L2 due to having that little data that fits in our L2 cache. In this case, Nsight Compute even provides warnings that indicate that our algorithm is not doing what it should do. They tell us very clearly that we read little data of our requested sectors and that we should try using more sectors. This kernel only accesses on average 1 sector out of the possible 4 sectors per cache line. This is exactly what we just talked about. To compare results more easily, we will set the current unaligned report as our baseline. Changing the axis from columns to rows is possible for this processing by simply changing the block dimension in the kernel launch. I predefined some optimization levels, so let's just launch with another command line argument, which takes care of this. Now, looking at the aligned reads, we immediately see that we are about 8 times faster. The speed of light section also indicates higher throughput with less gap between compute and memory. In the memory chart, our link between device memory and L2 is very close to peak performance. We load the expected amount of data from L2 to L1, and thinking about our cache hit rate, we also see what we expect. 75% L1 hit rate, which is due to requesting all bytes of the neighboring pixels in the neighboring threads. What else can we learn? Given the report, we know that the kernel is heavily memory latency bound, as we have to wait for device memory on each pixel's compute. In such cases, it can be beneficial to process multiple values in one thread. Let's check what we gain if we process 4 values After profiling, we see we did not gain much, if anything. Nonetheless, let's investigate the memory chart closer. We see that the request to global memory did not decrease, nor did the L2 to L1, which we also did not expect. But our L1 store to L2 increased and is not matching the expected 8 MB. Why is that the case? We are processing 4 pixels per thread now, but after every pixel we write 1 byte to our image. This needs to be flushed to L2, which artificially increases the throughput from L1 to L2, as we write with a new and 8 so little data at the same time. Threads that write to the same sector at the same time can actually be grouped together in one single write operation, but the wait period for this is very short. This brings us to vectorized loads, which is the last iteration on this kernel. We can use one UChar to load all values for 1 pixel, but we would still have to write back a single U and 8. Going with even wider operations ends up at reading 1 U and 4, which then can process 4 pixels in one thread and write back as one UChar 4. This resembles basically exactly the same as we've been doing in the multiple value kernel before. With both these optimizations, we have to make sure that we have enough work available to not reduce the number of blocks in our grid so much that we are no longer able to saturate the GPU. After reprofiling, taking another look at the memory chart, we see that our write to L2 is back to the expected 8 MB. In addition, we have no pressure anymore on the load store unit and did cut our requests by over 90%. This can also be seen when comparing the compute speed of light section of our aligned report and the vectorized load, as we have to do less indexing math on the pointers. Nonetheless, the kernel did not get much faster, as we were already limited by device memory in the previous version. Assuming our initial case of reading in columns is the way we must process our data, this approach can also be very helpful to make each load a little less costly. In conclusion, we can say that the best use of the memory workload section is to ensure that you load only as much memory as you really need, and aligning read accesses with sector or even cache line boundaries is very beneficial. For alignment issues, there will also be hints in the source section. This will help identifying memory stalls together with source correlation. This is part of a later tutorial. As a follow-up on this video, I can only recommend the excellent documentation inside our kernel profiling guide. That has even more details on the memory workload analysis section than I could ever cover in this video. Thank you very much for listening, and I hope you learned a lot about the memory subsystem of an NVIDIA GPU and how to profile using Nsight Compute.